So let's see, this is question 2 of the homework. And this whole spiel about the surface integral. What we care about is this expression here. And so this is a Gaussian surface because there's two. Oh, I see what. So right. So we got two hemispheres. That just means half balls. And this is sort of the side view. It's sort of like a cut through it. And then if I rotated it, I would see this ball here, and then surface 3 is flat. And then we can't see surface 2 in this picture. So they don't draw an E field line straight up and down, but they would be parallel to the E field line, so the A vector would be perpendicular. And so it's let's see, E dot dl. So cosine, yeah, it's the cosine when you do dot product. So if the angle of the well, let's see, we can draw this. We need a snipping tool so we can get this picture. And yep. Well, there we go. So oh boy, it's always something, huh? Let's see, where is the driver for this? Yep. And mapping this one. Well, that was easy. Let's see what happens. My old tablet just sort of, oh, look at that, it's working. Okay, so if I drew a vector straight up, which is a possibility, and for this surface, this is the A vector, and there's 90 degrees here. So the flux from surface C3, that's what I said, equals 0. Then, oh yeah, so C E equals C Q, I suppose, over R squared. And, just C over R squared, okay? That works. So now, surface 1, it's half of it's a hemisphere, and the area of a sphere is equal to 4 pi r squared. And so we say the integral of E dot dA, and in this case they're parallel, and let's see, R is a constant, so we can put this outside, and dA, and it's 1/2 of cosine of 0, and ultimately, well, it's EA, and that equals the flux, which is equal to sigma Q enclosed over Oh, gee, yeah, there it is. But they just wanted the flux, so we just need EA, and A just happens to be 1/2. So it's going to be C over R squared times 1/2 4 pi R squared. Isn't that convenient? They cancel out. Oh yeah, of course, the flux has to be the same. It's the same for, oh, wait a minute. Slow down. Right, you strictly speaking, if we have an expression, it should be R 1, and so C over R1 squared 1/2 4 pi R1 squared. So it's 2 pi C. And it turns out it's the same thing for surface 2. Because it's going to be C over R2 squared times 4 pi R2 squared. Yeah, okay. And I forgot the 1/2. Alright, so let's see. There it is. So it's 2 pi C, huh? 2 pi. Nope. I didn't click on alpha. I clicked on pi. C. And, okay. Ooh. 2 pi C. Okay. Now, it occurs to me that I might be hurting someone. You know, let's see. That did their homework on time, and now this someone hasn't finished their homework. So, let's see. Examples. Oh, we did that in class. Okay. Point charge. Alright, so maybe the fair thing is to not do the homework problems. Okay, let's or at least this way, if I might randomly hit a homework problem. Chapter 22. And let's see. Yep. Alright. Enable scrolling. Fit to the width. Okay. 22.3. Let's example 22.4. Figure 22.15 shows a field produced by 2 point. And find the election. Oh, we did that in class. Applications of Gauss's law. Right. And so, yeah. Right. See, there are not too many of them. Ah, this one. Okay. I should do this one. Oh, capacitors, huh? Okay. Charge, yep. We went over this. Ice pail. Okay. Let's find a problem. Applications. Ooh, an infinite is a radius. Oh, here we go. Hey there. Grad student just came in. A long line charge carrying uniform linear charge density. Wow. Find a location wall point, and it's only a 1-dot problem? Okay. And we can use a Gaussian online uniform linear chart runs parallel to and from a surface to large flat. Wow. So that would be all points where the field would be 0. So, well, I suppose, I don't know how to use Gauss's law to do this, but I've gotten interested, I've been intrigued. So, we'll get that, and, let's see now, so, get the problem, and, so, where is it? Shapes. So, we got a line charge. And, boy, I wonder if this thing has the 3-dimensional shape. Well, we'll be here forever. So, we'll just assume it's centered. Okay. So, let's remember the line chart, so lambda L is to Q. So EA equals sigma, no, Q enclosed over this. So the area of a cylinder is 2 pi, the outside, the end caps don't matter, 2 pi r times L, yeah, the circumference times the length. And so, let's see, 1 over A, Q enclosed, yep. And then the Q enclosed is the charge per unit length times L. So it's 1 over 2 pi RL, and this is lambda L, and there we go, it cancels out. So lambda over yep, here, and 2 pi. Oops, forgot the R. Okay, and then for a sheet, sigma over 2, yeah, okay. So that's constant. Now, thing is, so this, there might be there because, oh, interesting. So, and in this case, it's minus. So, lambda over 2 pi epsilon 0 r minus sigma, so we add them together, 2 epsilon 0 equals 0. So lambda over 0 r equals sigma over this, and we invert both sides, 2 pi over lambda equals 2 sigma 0 over 2 epsilon 0 sigma. So then ultimately R equals 2 0 times lambda over 2 pi epsilon 0. Oh, interesting. So 2 cancels, epsilon 0 cancels, and so that's weird, because I would have thought that we'd have to worry about it. We couldn't use R, but it makes sense. So since it's constant, it's just some distance where they equal each other. Interesting. And 22:38. I gotta get up to lab class in a minute. Let's see if I was right. Independent, yeah, it's independent of the distance between them. Lambda over pi sigma. What did I say? Lambda over pi. Oops, that's right. What happened to sigma? Oh, that's here. It's just messy. Huh. Yeah, it doesn't matter where the wire is. Isn't that interesting? Okay. Interesting. Do you feel... What? Well, I just need to know when they equal 0, right? So, alpha particle is positive. Well, it doesn't matter. I just need to know where it's 0. But why? Now I'm straight. Those illustrations are meaningless. It's not an X, because I think the line charge. Yeah, I don't get it. It doesn't. What they draw there doesn't matter. So we could imagine this: the line charge on the sheet, and then we have our 10 centimeters there. Flat plastic sheet on one side. Well, we assume we're going to stay on that one side. I don't know. That's kind of dumb. All right, so I got to get up to lab class. So I'll post this.